So trichloromethane and propanol are both organic liquids. Okay, so we know that is propanol, we know there's trichloromethane. The molecules within each liquid are attracted to each other by these permanent dipole interactions. You don't have hydrogen bond because you don't have a hydrogen bonded to fluorine or nitrogen or oxygen. Okay, but permanent dipole act in such a way that you have a delta minus on the oxygen, which is electronegative, and delta plus on the carbon, which is electrophilic. Alright, as for this, you have the 3 chlorine, which are electronegative, therefore withdrawing electron density from the carbon, and essentially there is inductively electron withdrawing. So meaning there's a delta plus there is enhanced due to these electron withdrawing chlorine atoms. When you mix that with propanol, you get a strong electrostatic attraction, which is essentially the permanent dipole interactions. Okay. So this student plans to perform an experiment. You want to investigate how strong is this attraction. Okay. What temperature change when you have equal volume of trichloromethane and propanol mixed together? When you mix them together, you form this electrostatic attraction, right? You form electrostatic attraction. So you are forming intermolecular force. So formation of intermolecular force, forming of bonds, whether it's intramolecular, which is covalent or metallic or ionic, or formation of intermolecular force, such as when you go from freezing, so when you go from liquid to solid, when you go from gas to liquid, so there is condensation and there is freezing. So those things are exothermic as well, because you bring the molecules closer together, you reform the intermolecular force, or you reform the ionic bond, or you reform the covalent bond, or you reform the metallic bond. Essentially, you form bonds, okay, just like you form intermolecular force for these simple molecules. When you mix them together, that will be exothermic. So your temperature change will be negative, meaning to say your final temperature will be higher than your initial temperature. So your final temperature will be higher than your initial temperature, meaning your temperature change is positive. Okay, meaning, well, I don't mean your temperature change, I mean the temperature change is positive. Or you can say something along the line that the temperature of the solution, when you mix them together, will increase. Okay, so somewhere along that line. Or temperature after you mix, temperature after mixing the solution. So either one would have been alright. Yeah, temperature after mixing increases. Okay, but that is the stating part. You gotta explain it now, as I mentioned. So the trichloromethane, I can use formula. It's probably faster if I use formula. So CHCl3 and CH3CO, CH3 form permanent dipole between them. Strong permanent dipoles between them. Therefore, formation of intermolecular force is exothermic. Exothermic meaning it will release heat energy. If it releases heat energy, then, well, if you release heat energy, then your solution will get hotter, which is what we saw, yeah? So your final temperature will be higher than initial temperature. It's the same as saying temperature after mixing increases. Either one would have been alright. Okay, so the student is given only the following apparatus as well as chemicals. So you have very simple stuff. You don't need to be super accurate, so you just are measuring cylinders. We are not going to use burette or pipette or whatever. What is the method that the student should use in this one experiment to find the temperature change when you mix the two things together? You gotta give details of the volumes of liquid used as well as any readings taken. Okay, They say outline the method. So we know that we earlier we were told we have to have equal volumes. Okay, we have to have equal volumes. So whatever volume we use for trichloromethane, we have to use it for propanol as well. Okay, the idea is you will have initial temperature before mixing, and then when you mix the second thing to the first thing, you will have the final temperature after it mixed. All right, okay, but the thing is you want to measure the maximum temperature and not simply let it warm up and then cool down again. That's not the point. You want to see what is the highest temperature it can reach after the mix. All right, of course after the mix they get hotter and then they will cool down again to room temperature. I mean, you saw it in your normal calorimetry experiments throughout your lower 6 practicals, so it's not a new concept to you, right? Whatever that gets hot will cool down again. So you really just want the maximum temperature. You get the maximum temperature by extrapolating your temperature against time graph in calorimetry, but then we are not doing calorimetry directly, so we can measure the highest temperature upon mixing or after mixing. All right, so what's the volume you should use? Because you are given 1 time 25 cm³ beaker, you see this measuring cylinder measures the volume of this and this. This beaker is for your reaction. So when you think about this is the only thing you're given. If you mix in 50 cm³ into this, that is not going to be enough. When you think about it, yeah, that is not going to be enough to put in 50 cm³. Okay, even if you put 25 cm³ of this, you still need 25 cm³ of this. You do not ever fill the beaker to the very top, never. Okay, so the volume used, I think sensible will be 10 cm³ of, because it says volumes, right? So 10 cm³ of trichloromethane. And then we know earlier it has to be equal volume of the trichloromethane and the propanol. The readings taken, we need the initial and the final. Actually it's not just the final, it's the final, not the final, it's actually the maximum. Okay, because final would mean like after it cool down. Maximum temperatures, maybe I should put them separately. Initial temperature before mixing, initial temperature of let's say trichloromethane. So I would have trichloromethane here, I will have my thermometer here. Okay, so I will have my temperature of the trichloromethane. Okay, initial temperature of the trichloromethane, and you will have another, but you only have one beaker, so I guess the other one you can put them in the measuring cylinder because you only have one beaker. So this is your 25 cm³ measuring cylinder. You do have 2 measuring cylinder, so you don't have to reuse them. You can use one for trichloromethane and use the other one for propanol. So of course you can put a thermometer in there, make sure you can work out the temperature of the propanol. Okay, initial temperature of the trichloromethane, if I set that one in a beaker, and then the final temperature, not the final temperature, you also need the initial temperature as well, because you got to make sure that the solution initial temperature, both of them are the same, right? That's why you need to leave the thermometer inside the solution for like 1 or 2 minutes, because you want, just like calorimetry, you have to leave the thermometer at the very beginning before you start your reaction, right? You want to make sure that the thermometer is actually recording the actual initial temperature of the solution. Yeah, initial temperature of the CH3 COCH3, and this one can be in a measuring cylinder, or you can have it the other way around. It does not matter. Yeah, but obviously you only have one beaker, so if you have the propanol in the beaker, then you need to have the trichloromethane in the measuring cylinder. Cannot mix them yet, because once you mix them, then they will give you the change in temperature already, right? Okay, what else do I need? I do need the volume. Volumes of the CHCl3 and also the CH3CO CH3 used. But of course, I already know there was 10 cm cube of each. I don't need time because this is not a rate of reaction. Really, it's just temperature. Oh, initial temperature, but I also need final temperature. Okay, final. Not final. I keep on saying final. Maximum. Okay, because the temperature is going to rise. So it's the maximum temperature of solution after mixing. After you mix them, what is the maximum temperature? So after you pour this from the measuring cylinder into here, what is the maximum temperature? What's the highest temperature you observe? All right. So what's the method we're going to use? We will have the CHCl3 in the beaker. So there's around 10 ml. Okay. Pour the 10 ml or 10 ml or 10 cm cube. I guess I should probably stay with 10 cm cube just to be consistent. Pour the 10 cm cube of the propanol CH3CO CH3 into the beaker. Okay, while keeping the thermometer. Already immersed and equilibrated, meaning to say it's settled to a fixed initial temperature prior to mixing. So basically, before you mix it, you already make sure the temperature on the thermometer doesn't change anymore. When that doesn't change anymore, you have reached an equilibrium. That thermometer is reading the temperature of the CHCl3 in the beaker. Then you pour in this one. Then you can see what temperature it rises up to. Yeah. Then record the temperature at regular time intervals. So just like you would do in a calorimetry experiment, you know, when you have calorimetry experiment, you will have that kind of table where you have time. Do we want time? We are not recording time. We are recording the temperature at the regular time intervals. Okay, so it could be second, could be minutes. Really, it's up to you. And then this is temperature in degrees Celsius. So essentially, like initially you have like 1, 2, 3, and then you don't do anything. You wait for initial temperature to settle. That is in here. You pour in this thing, and then you start recording the temperature rise after some time, etc., etc. Okay, these are all from your paper 3 actually. Yeah, from your practical experiments. Record temperature regular time intervals until can see has reached maximum. How would you be able to tell you have reached a maximum temperature? Well, that is when temperature falls again afterwards. Okay, so you know how in calorimetry you would have temperature and then you have time. Obviously you have the units, you have like and then temperature rise all the way up, and then it goes up, and then it comes down again. Okay, so we know that we have that, and this is spread over 2. Oh, no, you want to extrapolate it like that. Okay, so we extrapolate from the vertical line sometimes. So I'm not sure if we're gonna get the maximum temperature or not, but we can always draw a graph like this and we can extrapolate them afterwards. Alright, so I better just put it somewhere. Do I want to put it there? I can. I'll just leave it there. Okay, cool. And don't want that anyway. I'll leave it there. Okay. Yeah, so I mean, I've got my volumes, I've got my temperatures, I've got my method. I think that's probably as much as I could do, really. Alright, so these apparatus use lead to significant heat loss. Well, I mean, what do we have? We have beaker, and then that's it. We just mix them together. There's no even a lid or anything, right, to cover it to prevent heat loss. So if you want to reduce heat loss, well, as soon as after mixing, as soon as mixing in the other solvent, or in this case the reactant, I guess. No, they don't react, so it's not a reactant. Use a lid to cover the top of beaker. Then at least the lid can prevent heat loss. To prevent heat loss from the reaction to the surrounding, obviously. Yeah, okay. What else could you do? You know, like how we would have a beaker usually to support a polystyrene cup, and then we have cotton wool for insulation. But that is if you have a polystyrene cup, then you can support it on a beaker. But now you have a beaker, so what would you do? Well, instead of using a beaker, use a polystyrene cup. Then you can support it on a beaker. Alright, so there's another alternative you can do. Of course, you can also insulate the glass beaker. You can insulate them with cotton wool, which will prevent further heat loss. Alright, so but they only want one improvement. So you know, a lid is the best thing, is the easiest thing I could think of, because you could use a different apparatus. But yeah, I mean, this is what we have been offered, and they say what could you improve? You could of course change the apparatus to the polystyrene if you want to. Okay, something you'll be familiar with from doing a lot of calorimetry experiments, right? Okay, so next bit, trichlorometer and propanol are both volatile. Volatile means they boil easily, so low boiling point. Flammable is probably the easiest thing I can think about, because when they say precaution, so keep them away from fire. Keep them away from naked flame. Naked flame refers to, if anyone has any Bunsen burner around the lab, that is fire. Okay, as they are flammable. As they are both flammable and volatile. So if they are volatile, they become gas easily. If they become gas easily, they can fill up the air with vapor. So even though they are not so close to naked flame, but you might get the vapor of it, you know, lingering around in your lab. And whenever there's a naked flame, they can catch fire. That's very, very dangerous. Yeah. So step 1 change, apart from reducing heat loss. So apart from, yeah, so you can't use that again. Improve the accuracy of these experiments. So this experiment involve, you know, different volumes of the solution, and we are using measuring cylinder, which are probably not the most accurate thing to measure volume. All right, so I mean, they do have lines on the measuring cylinder. At least we know it's more accurate than beaker, but it is no more accurate than using a beaker, really. I mean, it's using a measuring cylinder, right? So you just want accuracy. So accuracy is to do with a better instrument. So you can use a burette or a pipette, because we are measuring a fixed volume, right? So your beaker was 25 cm cube, so I used 10 cm cube. I'm not sure if you know this. I know in a O-level, IGCSE or GCSE, you will have only used like 25 cm cube pipette, but there are certain A-level questions, practical questions, that involve you using 10 cm cube pipette. So 10.0 cm cube pipette does exist, right? But they are not as flexible volume as burette, which can, you know, measure out accurately different volumes that are not of regular intervals, right? So we are measuring 10.0 cm cube with pipette. We can measure 10.00 cm cube with burette, so they are far more accurate, all right, to measure out the volumes of the CHCO3, which is the trichloromethane, and the propanol required. They say state 1 change, they didn't say explain, so stating should have been more than enough for that 1 mark. In another experiment, we use, instead of volume, we use mass. Okay, instead of volume, we use mass, and we found the energy release is 1.67 kilojoule. This is not enthalpy, this is energy release. All right, calculate the number of mole of each compound. So you give you the MR, you have the mass. This is your mass over MR from your GCSE, from your IGCSE, from your O level, So mass over the MR, the propanol is again the mass over the MR. You see the data given here is 4 sig fig, here is 3 sig fig, here is 4 sig fig. So depending on what value I get, I can run it up to 3 sig fig or 4 sig fig. That would generally have been acceptable. Okay, I assume I would need the mole for my calculation further, so perhaps I can leave it as 4 sig fig. All right, so that run out to 0.3138 mole. 4 sig fig. I guess for 1 mark they can't really penalize you since they don't specify how many sig fig you should give this to, right? So it's 0.34052. So it's 0.3405 to 4 sig fig. Okay, I'm looking at this being 4 sig fig, and this one being 3 sig fig, and this one being 4 sig fig. Yeah. So it's trichloromethane, and the propanol is 0.3405. Okay. So previously we used the same volume of this and this when we mix them together. Here we use mass, and mass is not volume, and our mole is not the same simply because our MR are different, the mass are different as well. Yeah. Calculate the enthalpy change of the electrostatic attraction formed between the trichloromethane and the propanol. Okay. So we gotta think about the 2 different mole. We react 1 mole with 1 mole because when you look at the formation of this electrostatic attraction, this is between 1 molecule of it with another molecule of it, because this one has only got 1 hydrogen, which is delta plus. So what we're looking at is 1 molecule of this plus another molecule of this. So 1:1 give you 1 of these. But of course in solution you actually have a lot of these interactions that come together, but it always comes down to 1 of these delta minus with 1 of this delta plus, because in this molecule there's only 1 hydrogen delta plus. So because of the 1:1 reacting ratio to give you this interaction, and here you do not have 1:1 exactly. So based on what I just said, based on the 1:1 reacting, well, it's not reacting, it's you can call that interacting, okay, because it's forming the intermolecular force ratio. So we know the mole of CHCl3 is equal to the mole of, I'll just draw propanol skeletal formula, that's a lot faster. Alright, so therefore this one is slightly more than this. We can tell propanol is in excess. So propanol is in excess. Whenever we want to work out enthalpy change is kilojoule per mole, we do not ever use something which is in excess. Even in your calorimetry from AS level energetics, from AS level practical experiments, you would know that you always have to use the limiting reactant, the mole of something which is completely used up. Alright, so since there is an excess, therefore the CHCl3 is limiting. Okay, so limiting and excess are something you have covered in GCSE and also O level. So therefore our delta H, remember that your delta H, you are forming electrostatic attraction, your delta H is lesser than 0. This is the energy release, your reaction, which is your enthalpy change of the reaction, release energy. So we're looking at exothermic reaction. There's 1.67 kilojoule. There's 1.67 kilojoule. It will be negative because your reaction released the heat energy. Alright, it will be divided by the mole of the limiting reactant, the one which is completely used up. So that is 0.3138 mole. because that is the limiting reactant. So that gave me minus 5.3 to 186 kilojoule per mole. That is way too many significant figure. I think this is the last part that I usually do in a calorimetry. Okay, so I will convert this into 3 significant figure. But before I do that, I mean, you have seen that I have shown it to be slightly more significant figure. So that it's easier for me to check my answer afterward. So that it's easier for me to show the examiner that, you know, I've done the previous step all right, and, you know, when you check the answer, it's become easier and more efficient. Sign, value, unit. This is enthalpy change, yeah? Phew, that was quite a short question 1 actually, for 11 marks, alright? Suggest an experiment the student could carry out whether the number of moles of trichloromethane affects the temperature change. Well, we said that trichloromethane was fully used up, right? Trichloromethane was fully used up. So because this is what we are changing, you see, yeah, this is what we are changing. So this is what you want to change, all right? You want to change this. Therefore, this is your independent variable. Okay, we want to test, when we change the mole of trichloromethane, can that lead to a different temperature change? All right, so maintain the same, I guess, keep initial temperature the same, and you want to, no, initial temperature doesn't matter, because if the thing is cooler, it will still give you the same temperature rise, right? If this is the important factor here. So what are we not changing? Remember, we are mixing in the same volume of CHCl3 and same volume of propanol. So I don't want to change that because I just want the number of mole of trichloromethane to change. So keep the volume of whether the number of moles of trichloromethane affects the temperature change. So we've got to keep the volume of the propanol constant, because that is a variable that we don't want changing, because we want to monitor how changing the mole of CHCl3 would affect the temperature change, right? So keep the volume of propanol constant, and then change the volume of trichloromethane. And then when you change the volume of trichloromethane, then you will change the mole of trichloromethane, and then monitor or record if the temperature change, basically if the temperature change is the same or not. Okay, if the temperature change is different from, is the same or not, if the temperature change is the same as the previous experiment, where equal volume was used. Okay, if there is a difference, in fact, if there's a drastic difference in the temperature change, so that means changing the mole of trichloromethane by changing the volume of trichloromethane, that will affect the enthalpy change. That will affect the temperature change and therefore the enthalpy change. If the temperature change, however, is very small or is the same, even when you change the volume of trichloromethane, that means you're changing the mole of trichloromethane. That means it doesn't affect it then. Okay, so it's whether it's dependent or independent. I mean, it's whether this relationship is true or not depends on the experiment and the results that you get. Yeah.